Okay, good morning. Unfortunately, Mr. Cheng cannot make it here, so I'm giving this talk instead of him. The topic is the boulders on the asteroid surface, clues to the formation history of the top-shaped morphology. The motivation of this study is from the ongoing missions, the Osiris-Rex and the Hayabusa 2, and they are targeted asteroids, Bennu and Ryugu. Though in different sizes, they have very similar overall shape, like a top shape. Actually the common mechanism for the top-like shape formation has been long discussed because previous radar observations also discovered a lot of, several top-shaped asteroids. But this is the first time that spacecraft closely visited two top-shaped asteroids, and it means we do not only have the overall shape, and we also have the very detailed surface features from the images. So what we are going to do is try to connect the global reshaping process and the surface processes. One of the most constant feature is boulders distribution on the surface for both the Bennu and the Ryugu. And some of the boulders are very large that are unlikely to be the impact ejecta from cratering processes. So we consider these more like original fragments of the parent body for these bodies. So if we accept this, the co-evolution between the border motion and the regulus layer formation and the redistribution would be a good point to study. It may give us some clues to understand the geologic history of the top-like shape for all kinds of asteroids. And there are several distinct features for the distribution of the boulders. First, for both Bennu and Ryugu, the big boulders locate predominantly at the high latitudes, and from the very detailed features, like the fourth one, we can see that several big boulders are partly buried by the regulus grains, and there's an oblique with respect to the local surface. And for Ryugu, there's a very large boulder on the pole, which is famous, and the third, like as shown in the third image. So what we are trying to do is to build a numerical model that combines the border evolution and the regulus layer evolution. Here are some basics for the method we used as a classic soft sphere discrete element method, and it combines the normal and the tangential contact forces and the rolling, twisting contact torques, and also cohesive force as included. For the simulation settings, we accept assumption that the original body may have a stiffer interrail and is covered by the loose regulus on the surface. We notice this is a pretty much a symmetric problem. It means we don't have to put particles over the globe of the body, and we just do a narrow strip to see what it happens. And by doing this, we drop 2 million particles on the narrow strip and create a thickness of the original regulus layer. Here we use the particle size for about 1 meter, which is close to the real case. And the next step is that we put a massive cuboid on the surface to mimic the original borders on the Regulus layer. So the next step is we spin up the system to create a Yorp, to mimic the Yorp similar processes and to see what happened to the Regulus and what happened to the borders. Here, because we are using the SSDM method, the time step for integration cannot be very large. So we have to be very cautious to choose the spin-up time. Here we use a quasi-static path to be an indicator for this process. Like if the spin-up is slow enough, anytime during the spin-up we stop the spin-up processes, the motion of the Regulus will immediately stop. And that's what we call the quasi-static path. And we respect this as a standard. And by doing so, we spin up this body from a period 7.6 hours to 3.5 hours during a simulated time of 2 weeks, and to see the dynamical responses of the Regulus layer and boulder on surface. Here are the results for the Regulus layer. We can see before the spin reaches the critical spin limit, the whole structure keeps steady. And from the left figure, we can see that shear band forms. The color means the friction height. So we can see that after reaching the critical limit, the global landslide first happens near the mid-latitude region. And as this process continues, we can see from the left movie, we can see that the avalanche particles will deposit on the equatorial ridge. And in that case, mid-latitude Regulus will become thinner, and there would be a small area around the pore, which barely moves. It means there is a stable region. And as it continues, we can see that a typical equatorial ridge formed in this case. Here is a clear movie we colored by the latitude, and what we can see that landslide first happens on the mid-latitude, and the cliff collapse grows up to the high latitude region. As a summary of this process, we can see that first, the mid-latitude occurs the global latitude landslide, and the cliff collapse propagate from the mid-latitude to the high latitude, and the regular debris may deposit at the equator region, and there would be a stable region near the pole. And what happens to the borders? We consider four positions. First is near the polar region, the 87 degrees in latitude, and we can see that the Regulus barely moved, so the border is stable there. And for high latitude region, which is 75 degrees, and we see as the collapse grows to higher latitude, the border will sink into the dense floor of the particles and rotate as it is transported to lower latitudes. Similar process happens to the mid-latitude case, and in this case, the boulder is transported for a longer distance, and also it sink into the granular and rotate a little, make a oblique configuration at the end. And for the last case, it's an interesting case. The low latitude case, that finally the boulder is totally buried by the avalanche particles after the whole spin up. And we also compared the different friction parameters. We can show that for higher friction, the stable region around the pole is bigger than a low friction case. But the overall shape will still be a top-like shape. So in summary, we basically built a comprehensive numeric model to mimic the co-evolution of big boulders and motion on the surface, as well as regular scraping processes during the yaw spin up. And what we found is top shape and the distribution feeder of the boulders can be both the results of yaw spin up. And in particular, if we compare with detailed images of the surface, we can see that the large boulders that's halfway buried into the regolith, and there's outcrops and oblique configuration can also be the results, which is consist with our simulations. And the low density of the boulders near the equator could be a result of the barrier mechanism. It means originally the boulders may distribute uniformly after the whole spin-up process. The equatorial ones may be buried, and it makes a distribution like today. And that's all. Thank you. I'm ready for any questions.
Thank you, Ben. Unfortunately, we don't have time for questions, and